Today we are diving into something that sounds like pure science fiction, using a simple beam of light to read the hidden world of molecules. So how on earth is that even possible?
I mean, really think about that. It's an incredible idea, right? The secret is all wrapped up in this really subtle, super rare dance that happens between light and matter. And honestly, discovering it changed everything.
To get our heads around this, we have to start with the basics. What happens at the most fundamental level when you just shine a light on something? It's a process you see every single day, but it's holding a pretty amazing secret.
Okay, so imagine you're firing a stream of microscopic paintballs at a wall. Most of them are just going to bounce off, right? Well, that's pretty much what light does. When laser light hits a substance, its photons, the particles of light, just scatter. And that, right there, is our starting point.
But this is where things get really interesting. See, not all of those scattered photons are created equal. They actually have two totally different destinies. And one of them, well, that one is the key to this whole story.
So, the vast majority of photons do something called Rayleigh's scattering. The best way to think of it is a perfect bounce, a totally elastic collision. The photon zips in, bounces off, changes direction, but its energy, its color, stays exactly the same. But a tiny, tiny fraction of them do something else entirely, Raman scattering. This is an inelastic collision. The photon doesn't just bounce, it actually swaps a little bit of energy with the molecule it hits.
And when I say tiny fraction, I mean it. We're talking about one photon in a million. Just one. It's this incredibly rare event that holds all the juicy information we're after. It's like finding a single message-carrying needle in a haystack of a million perfectly ordinary ones.
So, who was the genius who first spotted this ridiculously faint signal? For that, we've got to jump back in time to the early 20th century.
That person was the brilliant Indian physicist Sir C.V. Raman. Back in 1928, he and his student K.S. Krishnan saw something nobody could explain, a faint, color-shifted light. He called it, simply, a new radiation. Now, he wasn't working in a total vacuum, of course. Scientists had understood that common Rayleigh scattering for decades, and another physicist had even predicted that this kind of inelastic scattering should exist a few years earlier. But Raman was the first to actually design an experiment to prove it was real. And that amazing feat earned him the Nobel Prize just 2 years later. All right, so here's the million-dollar question. How does that tiny little energy swap tell us what a molecule actually is? How do we go from a faint glimmer of light to a perfect chemical ID?
Here's the absolute key. Every single molecule is constantly vibrating. Its atoms are stretching, bending, and twisting around in very specific ways. These vibrations aren't just random either. They can only happen at precise energy levels. Think of it like a molecular song, and every single type of molecule sings its own completely unique tune.
Okay, so scenario 1. A photon from our laser comes cruising in and smacks into a molecule. It gives a little piece of its energy to that molecule, basically kicking one of its vibrations up to the next level. Now, because the photon lost energy, it leaves with a lower frequency. Its color is shifted. This whole process, that's called Stokes scattering. But what if the molecule our photon hits is already buzzing with extra energy? Well, in that case, the exact opposite can happen. The molecule can actually dump its extra vibrational energy into the photon, so the photon flies away with more energy than it started with. This is a lot less common, and it's called anti-Stokes scattering.
And this really shows you the challenge, right? The light from all that normal Rayleigh scattering is just overwhelmingly bright. It's like trying to hear a whisper in the middle of a rock concert. The Stokes and anti-Stokes signals we need are just incredibly faint in comparison. And the anti-Stokes signal is even fainter because, well, most molecules aren't just hanging out in an excited state.
But this is where it all comes together. The exact amount of energy the photon gains or loses is a perfect match for the energy of that molecule's unique vibrations. So by measuring these tiny shifts in energy, we can create a map of all the vibrational notes that molecule can play. And that map is its Raman spectrum, a totally unique, unforgeable chemical fingerprint. Okay, so we have this amazing tool for identifying molecules. What can we actually do with it? Let's take a look at how this incredibly rare effect has a massive impact on our actual world. The applications are just, wow, they're everywhere.
Raman spectroscopy is used all over the place, from basic chemistry labs to figure out molecular structures to atmospheric science and even in medicine to check tissue for signs of disease. It's used to boost signals in fiber optics and, get this, it lets scientists literally see the chemicals inside living cells without hurting them at all.
Which brings us full circle, back to our original question. How does that beam of light spot a fake drug? Well, it shines a laser on the pill, filters out all that boring Rayleigh light, and reads the faint Raman signal that comes back. It then compares that signal, that unique chemical fingerprint, to the known fingerprint of the real deal. If it's not a match, you've got a fake. It's that simple, and it doesn't damage the sample one bit.
The discovery of Raman scattering really opened up a brand new window into the molecular universe. It's an amazing reminder that sometimes the most important secrets are hidden in the faintest signals, just waiting for us to figure out how to listen. And it just makes you wonder, what other invisible secrets will light help us see next?